All right, hello everyone, and welcome to the third to last astronomy talk here. We have finally made it out to the scale of the universe. Today we're going to talk about the birth of the universe. Next week we will talk about the death of the universe. And we're going to talk about a bit of cosmology here, though hopefully without all of the math that goes into cosmology. So tonight's quote is, of course, a very famous one from Douglas Adams. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. So let's start with that creation of the universe. So we all know the name of the theory for the creation of the universe, and that is the Big Bang Theory. Not the TV show, but the actual scientific theory the TV show is named after. The term Big Bang was actually coined all the way back in 1949 by Fred Hoyle. You can actually go listen to this original BBC radio broadcast where astronomer Fred Hoyle called this sudden expansion of time and space a Big Bang. And so this theory states that everything that we see today, all the galaxies, the planets, you and me, all began as this hot collection of matter and light squeezed to a very, 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 very tiny point. And the Big Bang Theory has stuck around for so long because it does the job that all theories should do. It should describe observations successfully, and the Big Bang Theory definitely does. It describes how the expansion and cooling of that hot, dense matter and light gradually led to the creation of stars, galaxies, planets, and you and me. And it also explains several properties of our universe today that we can go look out at. Now, observations demonstrate that the universe is cooling as it expands, implying that it was much hotter and denser in the past. Calculating exactly how hot and dense the universe must have been when it was more compressed is much like calculating how the temperature and density of a gas in a balloon change when you squeeze it, except that the conditions are way more extreme. You see here in this plot, we've got temperature on the vertical axis and seconds since the Big Bang on the horizontal. Both of these are in log scale, in powers of 10. So all the way at the top left, at just the exact moment of creation, the temperature was 10 to the 32 Kelvin. That is a 1 with 32 zeros after it. Blazingly hot. But you can see that as time goes on, that temperature decreases very, very fast. Here, hopefully you can see my mouse here, is about 1 second after the Big Bang, all the way almost at the bottom right, and is in just a second, it is cooled from 10 to the 32 Kelvin to just about 10 to the 10, maybe 10 billion Kelvin. It didn't take long for the universe to cool. At the present day, it's a very cold 2.7 Kelvin. And you can even see that most of the universe's history, conditions were no more extreme than those found in many places in the universe today. Here, this green dotted line, I've marked out the temperature of the surface of the sun. And you can see from most of the universe's history, it's been much cooler than just the surface of the sun. But we can understand the physics of the early universe by applying the laws of physics to these temperatures and seeing what kind of crazy things were happening back then. One of the crazy things was the creation and annihilation of matter. So during those first few seconds, the universe was so hot that there was so much energy in the universe that photons could spontaneously transform into matter and vice versa. So two photons, two gamma rays come together and create a proton and a neutron. But then almost immediately, the proton and the neutron, or sorry, not a proton and a neutron, I should say an electron and a positron. These matter antimatter pairs would come back together and self-annihilate, giving us back those two gamma rays, which could then go on and recombine to create another matter antimatter pair. since the universe was filled with the necessary conditions for this stuff to happen, the early universe was constantly doing this, taking this blend of photons, matter, and antimatter, and just switching back and forth every minute second. I mean, we're talking fractions of a second it would do this. And although this sounds pretty chaotic, physicists have been able to recreate these conditions in the universe. We are in our particle accelerators. We have observed the behavior of matter and energy at temperatures as high as those in the early universe, when it was just 10 to the minus 10 seconds old, a 10 billionth of a second, giving us confidence that we do actually understand what was happening in the universe these early times. Now, our understanding, this is sort of a caveat, our understanding of what happened before a 10 billionth of a second is less certain, but we do have some ideas about what the universe was like a mere 10 to the minus 38 seconds old, and perhaps just a glimmer of what it was like at the age of just 10 to the minus 43 seconds. But these tiny fractions of a second are so small that for all practical purposes, we are studying the very moment of creation, the Big Bang itself. So not only was matter constantly being created and then annihilated, but there are also some forces involved here as well. We've talked about these fundamental forces before. Gravity is the one that's most familiar. Of course, it holds the planets and the stars and all the galaxies together in their orbits. It dominates at these large scales. So gravity is the one that we have the most familiarity with in our daily lives. Electromagnetism is another very familiar force. If you ever stick a magnet to your refrigerator, you know about that. Your computers, all of our electronics rely on the electromagnetic force. The electromagnetic force is far stronger than gravity, which is why when you study chemistry and biology, at the very root causes, even though you may never talk about it, it is electromagnetism that you're studying. Now, even though it's much stronger than gravity, you can see over here in my little table, you can see the relative strength column. If gravity is a strength of 1, then E&M, electricity and magnetism, has a strength of 10 to the 36, is much stronger. But we don't notice it in our daily lives because most objects are electrically neutral. There aren't, huge conglomerations of positively charged things hanging out there or negatively charged things. Everything's electrically neutral, so it's not that important on large scales. Then we get the nuclear forces. The strong nuclear force binds protons and neutrons together in the nuclei, and indeed actually binds the quarks that make up those protons and neutrons together. And then weak nuclear force plays a role in nuclear fission and fusion. You can see how strong those are. The strong force is the strongest, just slightly stronger than electricity and magnetism. Weak force, despite the name, is still stronger than gravity. Gravity is the weakest force in the universe. However, both gravity and electromagnetism work over supposedly infinite distances. Even though here I am on Earth, I am still feeling a gravitational force from a galaxy 45 billion light years away. It might be really, really small, but I still feel that force. Meanwhile, the strong and weak forces work on scales that are about the size of an atomic nucleus. They don't get much further out. And you can see the abbreviations for the current theory. General relativity is how we describe gravity. Quantum electrodynamics, or QED, is how we talk about electricity and magnetism. Quantum chromodynamics is how we talk about the strong force, and the electroweak theory is how we talk about the weak nuclear force. And you might notice that if you go ask any science communicator about these forces, we got great answers for gravity, electromagnetism, a relatively good answer for strong, but it's a relatively weak explanation for the weak nuclear force, which is why I'm reminded of this XKCD comic. There are 4 fundamental forces between particles: gravity, which obeys this inverse square law; electromagnetism, which obeys this inverse square law, and also Maxwell's equations; 3, the strong nuclear force, which obeys, it holds protons and neutrons together, it's strong; and 4, the weak force, radioactive decay. That's not a sentence, you just said radio. And those are the 4 fundamental forces. That's pretty much all you can get out of a science communicator. Now, those four forces are pretty dang different from each other. But our current theories actually predict that they might just be different aspects of a smaller number of forces. And so we think that in the early universe, in those high temperatures, those forces, those four forces, would be much less distinct. So here's a plot of the forces in the universe based on their relative strength. Excuse me. Where on the vertical axis is the relative strength. So we got gravity down here, weak force, electromagnetism, and the strong force. On the bottom horizontal axis is the temperature increasing towards the right. On the top horizontal axis is the time since the Big Bang, decreasing to the right. So here in our late universe, our present day, we've got four forces: gravity, weak force, electromagnetism, and the strong force. But our theories state that if we raise the temperature a little in the universe, then actually the electromagnetic and the weak forces should merge to form the electroweak force. At even higher temperatures, the strong force should join the electroweak force, and the models that describe this sort of superforce are called grand unified theories, or GUTs. And then perhaps at even higher energies, gravity might merge with the other forces. That kind of super force there at the far right, where all of the four forces are merged together, is the subject of a lot of work. Current ideas for linking all those four forces include supersymmetry, superstring, supergravity, and the mythical theory of everything. That if we have this equation that describes how these four forces merge together, then we should be able to describe how everything works. Einstein was working on it towards the end of his life. He couldn't get an answer, and many people since then, and still working today, haven't yet reached a grand theory of everything. But if these ideas are correct, then the universe was governed solely by this mythical superforce in the first instant after the Big Bang. And so as the universe cooled and expanded, that superforce split into gravity and the grand unified theory force, which then further split to the strong and electroweak forces, and then ultimately all four forces became distinct. And as we'll see in a moment, these changes in the fundamental forces probably occurred before the universe was 1/10 billionth of a second old, and had some drastic consequences for the evolution of our universe. So let's talk about the evolution of the universe, starting from the Big Bang and walking through these sort of eras. Cosmologists describe the history of the universe in eras depending on what the physics like, what the conditions were like in the universe at that time. So we will start off with the smallest instance of time, the Planck era. So from the time of the Big Bang, time 0 to just 10 to the minus 43 seconds after the Big Bang. So here we're kind of just guessing at this. So according to quantum mechanics, the universe should have been filled with energy fluctuations as light turns into particles and vice versa very rapidly. Now, because energy and mass are equivalent, remember Einstein's famous equation, E equals mc squared. Energy is mass times the speed of light squared. Those energy fluctuations must have generated some rapidly changing masses, which would generate a rapidly changing gravitational field. And that would cause space and time to be randomly warped. And these fluctuations are predicted to have been so large that our current understanding of physics can't explain them. We can't describe what might have been happening. The main problem is that we lack a theory that unifies gravity with quantum mechanics. General relativity and quantum mechanics give two different answers for when we want to investigate gravity on the small scales. So we're still working to get at that theory. Perhaps someday, we will be able to merge these theories of the very small and the very big into a theory of everything. But until that time, we can't accurately describe the universe during the Planck era. But nevertheless, we do have some idea of how the Planck era ended. As the universe expands and cools, once that temperature drops beyond 10 to the 32 Kelvin, gravity will split from the superforce, and the Planck era will end. my analogy to the way ice crystals form as liquid cools, we will say that gravity froze out at the end of the Planck era. Right, next comes up is the GUT era, the Grand Unified Theory era, from just at the end of the Planck era to 10 to the minus 36 seconds. Now here, the Grand Unified Theories predict that the strong, weak, and electromagnetic forces were merged together and operated in concert with gravity. Now, thankfully, our physics has gotten far enough to be able to say something about the GUT era, more than what we could say about the Planck era, but admittedly, none of those ideas about what's happening in this small section of time in the universe have been tested. Now, if our theories are correct, then at the end of the GUT era, then the freezing out of the strong force from the electroweak forces might have released a huge amount of energy. And this energy went in to cause a rapid, dramatic expansion of the universe. And we call this sudden dramatic expansion inflation. And it caused, in a mere 10 to the minus 36 seconds, pieces of the universe the size of an atomic nucleus may have grown to the size of a solar system. The volume of the universe increased by 10 to the 78 times its previous volume. This would be equivalent to taking a DNA molecule out of a skin cell and expanding it to 10 light years long in the fraction of a second. Now, this might sound completely bizarre, but towards the end, we'll discuss how it actually explains a lot of important features of today's universe. So keep this in the back of your head. We'll come back to it. After the GUT era, now that we are governed by just three forces, gravity, the strong force, and the electroweak force, we've entered the electroweak era. So 10 to the minus 36 seconds to 10 to the minus 10 seconds. Here, we've got these three distinct forces. And light is filling all of space, constantly producing matter and antimatter that then combine to reproduce light. And the universe will continue to expand and cool until it reaches a temperature of about 10 to the 15 Kelvin, when it reached an age of just 10 to the minus 10 seconds. This is cold enough for the electromagnetic force and the weak force to split. Admittedly, this temperature is still 100 million times hotter than the temperature in the core of the sun today, but it was low enough for this to happen. And we do have direct experimental evidence of the conditions that happened in the electroweak era. So the theory that unified the weak and electromagnetic forces, which was developed in the 1970s, predicted the emergence of new types of particles called the W and Z bosons at temperatures above the 10 to the 15 Kelvin temperature that pervaded the universe during this time. And in 1983, particle accelerator experiments reached the energies equivalent to these high temperatures for the first time, and those particles popped up just as we had expected them to, produced from the extremely high energy in accord with E equals mc squared. And so we do have this direct experimental evidence concerning the conditions of the universe in this electroweak era. We do not have any direct experimental evidence of conditions before this time. So our theories concerning the GUT era and the Planck era are just speculative, essentially, more speculative than what comes after here. So now, once we're done the electroweak, we enter the particle era from 1/10 billionth of a second to just a millisecond. During the early parts of this particle era, photons were constantly turning into these bizarre and exotic particles that we no longer see freely existing in the universe, including quarks. Remember, we talked about quarks several weeks ago. These are the particles that actually make up protons and neutrons. So over there on the right, you see a proton is made up of 2 up quarks and a down quark, and a neutron is 1 up and 2 down quarks. There are also 4 other types, so charm, strange, top, and bottom. This is where scientists, decide to have some fun names for once. And these were freely floating around in the universe. We don't see them floating around now. Once the temperature reached 10 to the 12 Kelvin, a trillion Kelvin, 1 millisecond after the Big Bang, it was no longer hot enough to spontaneously produce these matter-antimatter pairs. Now, what's really interesting is that we've got a universe full of matter. There is no antimatter, no huge pockets of antimatter that we think exist in our universe. Yet somehow that came out of reactions that only produced one matter particle for every one antimatter particle. And if that were true, then the universe would have contained an equal number of matter and antimatter particles. And those pairs would have annihilated, leaving only photons and no matter. We wouldn't be around to discuss this at all. So the fact that the universe contains matter tells us that something broke this symmetry. For every billion antimatter particles, there is a billion plus one matter particles, and we are the result of that plus one. It's very weird. We don't know what broke this symmetry. But thankfully it did, so we have time to ponder why it did. After the particle era, we reached the era of nucleosynthesis. From about a millisecond after the Big Bang to now we're at 5 minutes. The universe is only 5 minutes old so far. So now that all the antimatter is gone, the leftover matter can now start to fuse together. The temperature in the universe is still hot enough for fusion to happen all throughout the universe. And so they're going to make the first nuclei. But the problem is that gamma rays would blast them apart as soon as they were made. This sort of just happened off and on for about 5 minutes until the universe had expanded so much that fusion no longer occurred, even though the temperature was still hotter than the core of the sun. And so when fusion ceased across the universe, it was 75% hydrogen and 25% helium by mass, as well as a trace of deuterium, which is hydrogen with a neutron, and lithium, which is the next element after helium. So except for the small proportion of matter that stars later forged into heavier elements, the chemical composition of the universe remains much the same today. It's still about 75% hydrogen and 25% helium. And here down the right, you see a reaction diagram of all the different reactions that were happening during the era of nucleosynthesis. So we've got mostly hydrogen and helium in red, 75 and 25%, but then trace amounts of deuterium or hydrogen-2, trace amounts of helium-3, and even smaller amounts of lithium-7. No beryllium, because beryllium would always decay into lithium-7. And we'll talk about nucleosynthesis much more in a little bit. And now we've created all of the nuclei. We're now in the era of nuclei. And this lasted for a long, long time, from 5 minutes to 380,000 years after the Big Bang. So after fusion ceased across the universe, the universe is essentially nothing more than just a hot ball of plasma of hydrogen nuclei, helium nuclei, and a bunch of free electrons. That is, electrons not attached to a nucleus. We haven't formed atoms yet. And this remained the same for almost 400,000 years. And throughout this entire era, photons would bounce rapidly from one electron to the next, not getting very far. Basically, anytime the nucleus captured an electron, a photon would hit the electron, ionize it, and then move on to the next thing. And this happened for hundreds of thousands of years. The era ended when the temperature fell to about 3,000 Kelvin. And that was cool enough for hydrogen and helium to capture electrons for good, forming atoms, making the entire universe electrically neutral. And so the universe became transparent as photons could free stream. They were no longer bouncing around different nuclei. This results in the cosmic microwave background radiation, which we will talk about in a little bit. Then after that is pretty much what we're left with. We've got the era of atoms and galaxies. The era of atoms, when the universe consisted of a mixture of neutral atoms and plasma, along with a large number of photons. And because the density of matter in the universe differed slightly from place to place, gravity slowly drew atoms and plasma into higher density regions, which assembled into those protogalactic clouds we talked about a few weeks ago. Stars then formed in those clouds, and those clouds subsequently merged to form galaxies. And so the first full-fledged galaxies had formed by the time the universe was about 1 billion years old, beginning what we call the era of galaxies, which continues to this day. Generation after generation of star formation in galaxies steadily builds elements heavier than helium and incorporates them into new star systems. And some of these star systems develop planets, and on at least one of these planets, life burst into being a few billion years ago. And now here we are thinking about it all. And here's just kind of a summary of the different eras that we've talked about, all the way from the Planck era towards the left to the GUT, the electroweak era, the particle era, building up atoms and nucleosynthesis, and then eventually the era of nuclei and where we all are today. All right, so that's kind of the story of the universe so far. Now let's talk about what evidence we have for all of this. So there are two big pieces of evidence that help prove the Big Bang Theory. And the first one is observations of the thing that's known as the cosmic microwave background. So back in 1965, two engineers, Arno Penzias and Robert Wilson, you can see them there at the bottom right, they were working at Bell Laboratories in New Jersey, and they were working on this microwave antenna, this kind of bell-shaped radio. Shoehorn, sorry, not bell-shaped, shoehorn kind of shaped radio antenna. And they were trying to calibrate it. It was a microwave antenna trying to calibrate it for satellite communication, but they kept finding this noise that they couldn't get rid of. I mean, they tried everything. They even like deep cleaned the pigeon crap off of this antenna, but the noise still remained. And they found it in every measurement they made, and they found it no matter in what direction they pointed the antenna, indicating that it came from all directions in the sky and ruling out that it came from any particular astronomical object or even from Earth. They were very confused. But thankfully, nearby at Princeton University, physicists were calculating the expected characteristics of the radiation left over from the heat of the Big Bang. This was first predicted by George Gamow and his colleagues in the 1940s. They concluded that if the Big Bang had really happened, then this radiation should be permeating the entire universe and would be detectable in the microwave spectrum. And so this Princeton group soon met with Penzias and Wilson to compare notes, and both teams realized that the noise that Bell Labs was detecting with the antenna was the predicted cosmic microwave background, the first strong evidence that the Big Bang actually happened. And Penzias and Wilson did end up winning the Nobel Prize in Physics in 1978 for this discovery. It's a huge, huge, piece of the puzzle for the Big Bang. So let's talk about what it actually is, though, because I keep showing you this picture. What is that picture? Well, the CMB, the cosmic wave background, the CMB, consists of microwave photons that have traveled through space since the end of the era of nuclei, 380,000 years ago, when electrons joined with the nuclei, thus allowing photons to free stream. And so with very few free electrons left to block the photons, most of those photons have traveled unobstructed through the universe ever since. So you can see over here, when the universe was a bit younger, much hotter, photons couldn't get very far. These little wavy lines couldn't get very far before they hit an electron, were randomly sent some other way. But once the universe cooled and those electrons joined with nuclei, then there weren't many free electrons, and those photons could just go in a straight line without hitting anything. And that's what we're seeing from the cosmic microwave background, those original photons from 380,000 years ago. Now, since the CMB comes from the heat of the universe itself, it should have a perfect black body spectrum at a temperature of about 3,000 Kelvin, similar to the temperature of a red giant star. The spectrum of that cosmic microwave background, therefore, should have originally peaked using Wien's law. We talked about that in like lecture 5 or something. Go back and look at that. Using Wien's law, we can calculate at what wavelength that spectrum should have peaked. And it should have peaked at around 1,000 nanometers. That is firmly in the infrared, I believe. However, the universe has also expanded by about 1,000 times in size since then. So the CMB should be cosmologically redshifted at about 1,000 nanometers times 1,000, or a million nanometers, or essentially just 1 millimeter, which is firmly in the microwave range. And for the same reasons, those CMB photons that were at 3000 Kelvin have now cooled by a factor of 1,000 and are now at about 3 Kelvin. So to detect this, this is one of the most well-measured black body spectra that we have. The blue line is what the theory tells us. The red plus marks are what the data tells us. The error bars on here are so incredibly small. This is an astounding result that it fits so well. That there's no deviation between theory and observations. That is an excellent, supporting piece of evidence that we're on the right track. Now, in the early 1990s, a NASA satellite called the Cosmic Background Explorer, otherwise known as COBE, in 1992, was launched to test these ideas. And the results were a stunning success for the Big Bang Theory and earned the 2006 Nobel Prize in Physics for the team leaders of COBE, George Smoot and John Matter. What you see here is kind of an all sky map, a temperature sky map. Now, the entire temperature of the microwave background is about 3 Kelvin. It's actually about 2.73 Kelvin. But there are small variations in that. And so if you subtract out that 2.73 Kelvin, you can get those small variations. Essentially, is a point, we'll just round it up to 3 for simplicity, is some patch on the sky 3.00001 or 2.9999. That's what we're talking about when we see these kind of red and blue maps. And you can see it's kind of a poor resolution. If we were seeing the Earth at the same resolution as the COBE map, then yeah, we could make out North and South America, Antarctica, Australia, and then just Afro-Eurasia. But certainly it's very blurry. Later on, COBE had some successor missions. The first one was the Wilkinson Anisotropy Probe, or WMAP, in 2003, where we got much better. You can see the resolution has increased significantly. And we can now see coastlines. It's still a little blurry, but we can now see that Afro-Eurasia is actually 3 continents. Well, 2, because Europe and Asia are split for cultural reasons, but we can see Africa and Eurasia now. And you can see maybe Florida off North America. We can see a few of the larger islands. And then following WMAP, the European Space Agency sent up the Planck satellite in 2013, and it was an even better resolution. Now we can fully see tons and tons of features on the Earth. Let's zoom in a little bit to re-illustrate that. Back with WMAP, good resolution, but comparatively to the Earth, Cornwall and Wales just kind of blend into England. We lose the Boot Formation off of Italy. We can't see the smaller islands in the Mediterranean. Greece certainly just looks like a weird little jut out. But with Planck, suddenly we can see Wales. We can even see the small islands of Crete and Cyprus, Sardinia. And you can see Sicily now with much better accuracy. These little variations are just in a few parts of 100,000. These are small variations. And these slight variations also represent a predictive success of the Big Bang Theory. So recall that our theory of galaxy formation depends on the assumption that the universe was not quite perfectly uniform. Some regions of the universe must have started out slightly denser than other regions, so they could serve as seeds for galaxy formation. The small variations in the temperature of the cosmic microwave background indicate the density of the early universe really did differ from place to place. In fact, detailed observations of these small temperature variations are very important to the studies of galaxy evolution, because all large structures in the universe are thought to have formed around the region's slightly enhanced density. Measuring the patterns of variations in the cosmic microwave background therefore tells us both about what must have happened at even earlier times to create the variations and about the starting conditions that we should use as models in galaxy evolution. All right, the other big thing, aside from this being the other thing that supports the Big Bang Theory, is nucleosynthesis, the abundance of the elements. Everywhere in the universe, about 3/4 of the mass of ordinary matter, not including dark matter, is hydrogen, and about 1/4 is helium. The Milky Way's helium fraction is about 28%, and no galaxy has a helium fraction lower than 25%. And so although helium is produced by hydrogen fusion in stars, calculations show that this production can only account for a small proportion of the total observed helium. We therefore conclude that the majority of the helium in the universe must already have been present in those protogalactic clouds that preceded the formation of galaxies. And the Big Bang Theory makes a very specific prediction. So to see why 25% of ordinary matter became helium, we need to understand what protons and neutrons were doing during the 5-minute era of nucleosynthesis. So early in this era, the universe was at the very scorching temperature of 100 billion Kelvin, 10 to the 11 Kelvin. At this temperature, reactions could transform protons into neutrons and vice versa. So up at the top right, one of these reactions, if we take a neutron and add a positron, those merge together and we get a proton and an electron neutrino. And the opposite can happen, where those two things merge back together to form a neutron. I keep doing that, sorry. As long as the temperature remains this high, the number of protons and neutrons in the universe would remain equal. But as the universe cools, these reactions actually started to favor protons. And the reason for that is that neutrons are slightly more massive than protons. So it takes more energy to make neutrons, and that was starting to become unavailable. Plus, turning a neutron into a proton, because of that difference in mass, actually releases energy, thus being a favorable reaction. It's the same reasons why hydrogen fusion into helium releases energy, and it works like that up until you get to iron, when suddenly it doesn't release energy. It actually takes energy. So neutrons were changing into protons, but the protons were not changing back. And so for the next few minutes, the universe was still hot enough for nuclear fusion to happen. Neutrons and protons would combine to form deuterium, which is a hydrogen, which is a proton and a neutron together. And deuterium would fuse with a proton to form helium-3. So here's that sequence of reactions. So we've got deuterium, and then add a proton, and we get a helium-3 nucleus. Now, the thing is, a gamma ray would usually come along and split all that up and ruin all the hard work that the universe just went into. But as as the universe slowly cooled over these few minutes, fusion began to finally create these long-lasting helium-4 nuclei when the universe was about a minute old, and it cooled to a temperature at which it contained very few destructive gamma rays. Calculations show that the proton or the neutron to proton ratio should have been 1 to 7. That is 1 neutron for every 7 protons. And all available neutrons would be captured into helium-4 nuclei. So here I've got 14 protons and 2 neutrons. Now those 2 neutrons would take 2 of those protons and make a helium-4 nucleus. And what do we have left? We've got 12 protons with an atomic mass of 12, and 1 helium-4 nucleus with an atomic mass of 4. And that ratio of 12 to 4 is also 75 to 25%. Thus, the universe should have had a composition of 75% hydrogen and 25% helium by mass at the end of the era of nucleosynthesis. This matches the observed helium ratio strongly enough to support the Big Bang Theory. Exactly matching the observations. Now, why no heavier elements? Well, by the time stable helium-4 had been produced, the temperature and the density in the universe already decreased enough for processes like carbon fusion to happen. There were a few reactions between the very rare tritium, hydrogen-3, and the also rare helium-3. And so we got a little bit of lithium-7, but that was rare. Aside from hydrogen, helium, and lithium, all the other elements were forged much later in the nuclear furnaces of stars, except for beryllium and boron, which are heavier than lithium, but lighter than carbon, and they were created later when high energy particles broke apart heavier nuclei that formed in stars. So here you can see a sort of timeline for when things were happening. So these two black lines up here, the topmost one is just a proton, it's just hydrogen. The next one is neutrons. And you can see that about, this is log, so 100 seconds in, that's just, almost 2 minutes in, suddenly all those the number of neutrons drops. But the number of deuterium, this red line, helium-4, this green line, hydrogen-3, helium-3, all these jump up as soon as those neutrons go down. The deuterium gets used up to make helium-4. The helium-3 kind of sits around. This hydrogen-3 decays or gets used up. You can see how we end up with just up here at the top, mostly hydrogen and helium-4, with just a smattering of other slightly heavier elements. That's why the universe is mostly hydrogen and helium. And this agreement between observation and theory is a huge plus in the Big Bang Theory's wheelhouse. Now, when we discussed the eras of the universe, we noted that the universe was supposed to have undergone this rapid period of expansion that we call inflation, which happened at the end of the GUT era, when the universe was just 10 to the minus 38 seconds old. But now let's try and explain what happened and why we actually do need inflation in our theory of the Big Bang. So there are three big questions that we still have not yet explained in our little talks. We've tried to explain them in physics, just in our little talks. So first of all, where did the density enhancements that led to galaxies come from? So recall that successful models of galaxy formation start from the assumption that gravity could collect matter together in regions of the early universe that had slightly enhanced density. We know from our observations of variations in the cosmic microwave background that such regions of enhanced density were present in the universe at an age of 380,000 years, but we haven't yet explained how those density variations came to exist. Also, why is the large-scale universe nearly uniform? Although the slight variations in the cosmic microwave background show that the universe is not perfectly uniform on large scales, the fact that it is smooth to within a few parts in 100,000 is remarkable enough that we would not expect it to have occurred by pure chance. And why is the geometry of the universe flat? Einstein's general theory of relativity tells us the overall geometry of the universe can be curved like the surface of a balloon or a saddle. However, observational efforts to measure the large-scale geometry of the universe have not detected any curvature. As far as we can tell, the large-scale geometry of the universe is flat, which means it is at the precise balance point between being curved like a balloon and curved like a saddle. This precise balance is another fact that is difficult to attribute to chance. So taking a scientific approach to the early universe demands that we seek answers to these questions that rely on natural processes, and the hypothesis of inflation provides some answers. That is, if we assume inflation occurred, then we find that the density enhancements, large-scale uniformity, and flat geometry are all natural and expected consequences. But notice that that inflation is a scientific hypothesis because it is testable with observations we can perform today. And confidence in the hypothesis is growing because it has passed all the tests that we've given it so far. So the first question, where do these density enhancements come from? Well, quantum mechanics tells us that on very small scales, the energy fields at any point in space is always fluctuating. It's always sort of bubbling like this, particles popping in and out of existence. And these tiny ripples could be the origin of the density enhancements, but their sizes are too small to explain the cosmic density enhancements on the cosmic microwave background. However, with inflation, ripples the size of an atomic nucleus could be stretched to the size of the solar system. making them large enough to account for the density enhancements that led to the growth of galaxies. If that's the case, then the large-scale structure of today's universe started as just these tiny quantum fluctuations just before the period of inflation. Well, it also explains uniformity. If you look at the cosmic microwave background on opposite sides of the sky, well, let's back up. So imagine observing the CMB in a certain part of the sky, and you are seeing microwaves that have traveled through the universe since the end of the era of nuclei, just 380,000 years after the Big Bang. You are therefore seeing a region of the universe as it was some 14 billion years ago, when the universe was only 380,000 years old. Now imagine turning around, looking at the background radiation coming from the opposite direction. You are also seeing this region at an age of 380,000 years, and it looks virtually identical in temperature and density. The surprising part is this: the two regions are billions of light years apart on opposite sides of our observable universe, but we are seeing them as they were when they were only 380,000 years old. They can't possibly exchange light or any other information because the signal traveling at the speed of light has not had time to travel from one region to the other. So how do they have the same temperature and density? So for example, here, microwaves from A and microwaves from B have only just met each other at our point. They haven't yet, microwaves from A have not yet reached microwaves from B and vice versa. So why are they the same temperature and density? Well, the inflation hypothesis answers this question by saying that even though the two regions cannot have had any contact since the time of inflation, they were in contact prior to that time. Before the onset of inflation, when the universe was 10 to the minus 38 seconds old, the two regions were less than 10 to the minus 38 light seconds away from each other. Light traveling at the speed of light would therefore have time to bounce between the two regions, and this exchange of energy equalized their temperatures and densities. And then inflation pushed these equalized regions to much greater distances, far out of contact with each other. Like criminals getting their story straight before being locked in separate jail cells, the two regions and all other parts of the observable universe came to the same temperature and density before inflation spread them apart. Right? That explains uniformity. And what about geometry? So remember that Einstein's general theory of relativity says that matter can curve the structure of space-time to be either flat or critical, spherical or closed, or saddle-shaped or open. And the overall geometry of the universe depends on the average density of matter and energy. If the combined value is equal to the critical density, then the universe will be flat. And for all intents and purposes, it is very close to the critical density. The observations are. So we do think our universe is pretty flat. Why is that, though? Well, inflation explains why the geometry is flat, since a rapid expansion would smooth out any curvature the universe had to the point that any remaining curvature would only be visible on sizes larger than the universe. Just like you don't know about the curvature of the Earth by just walking around in a park down the street. You have to get to sizes larger than the Earth itself to start to be able to see the curvature of the Earth. Similarly, maybe the universe is just so large, we have to get to sizes larger than the size of the universe to see any potential curvature. So inflation therefore makes the overall geometry of the universe appear flat, which means that the overall density of matter plus energy must be very close to the critical density. So now, this all is well and good, but did this actually happen though? Well, the strongest tests for inflation come from the CMB, since that is a map as to where the density enhancements were. Models can tell us how inflation should have distributed everything, and we can compare the model to observation. So this figure is an analysis of the temperature variations observed in Planck in the cosmic microwave background, along with additional data from other microwave telescopes. The graph shows how the typical temperature differences between patches of sky depend on their angular size on the celestial sphere. The dots represent the data from the observations, and the red curve shows the inflation-based model that fits the observations. Notice how excellent that fit is between the model predictions and the data. Moreover, this same model often makes specific predictions about other characteristics of our universe, such as its composition and age, and these also agree well with observations. The general agreement between models and observations provides persuasive evidence in favor of the Big Bang in general, and also inspires confidence in the hypothesis of inflation. So some process very similar to the inflation hypothesis probably did happen in the early universe, although the details are still being worked out. Many astronomers and physicists do believe that inflation happened. All right, so this is all well and good, but as always, don't just take my word for it. You can think about this for yourself. Because back before we knew that the universe was expanding, back before Edwin Hubble's time, scientists used to believe that the universe was static, infinite, and homogeneous, that it wasn't changing, it was infinitely big, and it was the same everywhere. But that led to something called Olbers' paradox, named after German astronomer Heinrich Olbers, even though other people like Johannes Kepler had thought about this before Olbers did. He stated that such a universe, one that is static, infinite, and homogeneous, would have an infinite amount of stars, and so then the night sky would be blazingly bright instead of dark, because if the universe is infinitely old, it's unchanging, and is the same everywhere, then that means there should already be enough time for light to travel from faraway stars in any direction and reach our eyes. So the night sky shouldn't be dark, but should instead be filled with the light from all of the stars in the universe. We shouldn't be able to look up in the night sky and see any darkness. It should be blazingly bright. So the only resolvable answer to this paradox is either about something about those assumptions, that static, infinite, and homogeneous, something about those assumptions must be wrong. Either the universe has a finite number of stars, or the universe changes over time in some way that prevents us seeing an infinite number of stars. Well, the Big Bang Theory tells us that we only see a finite number of stars because the universe began at some point. There may be an infinite number of stars, but we can only see those within our observable universe. So we can only see a finite number of stars, despite there being probably an infinite number of them. Oddly enough, one person was very prescient for his time and got to this answer before the astronomy community did. And that person was none other than the Edgar Allan Poe in his one sort of nonfiction book, Eureka, back in 1848. He wrote in that book, were the succession of stars endless, then the background of the sky would present us a uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. Now, this may be so, who shall venture to deny? I maintain simply that we have not even the shadow of a reason for believing that it is so. So with that, we will end it tonight. Next week, we'll talk about dark matter, dark energy, and the death of the universe. It'll be the penultimate talk. And then after that, we'll do kind of an overall summary, kind of bring it all home. So with that, I will wish you all good night. Make sure to like, comment, subscribe. Feel free to ask any questions you might have in the comments or direct message me. I'll be happy to answer them. But I will see you all next week.